Hello and welcome to Math Zone African Motives. Today, we're diving into Module 4, Unit 4.2, Algebraic Graphs. In this tutorial, we are going to focus on a specific type of graph, the semicircle. Our goal is to understand the general forms of semicircular equations, identify their key features like domain and range, and learn how to sketch them. By the end of this video, you will be able to recognize the 4 different semicircular graphs and determine their exact position on a coordinate system. We'll start with the general form you'll encounter most often. It looks like this: y equals the square root of r squared minus x squared. To understand where this comes from, let's square both sides of the equation. Squaring it gives y squared, and squaring the square root term gives us r squared minus x squared. If we rearrange this, we get x squared plus y squared equals r squared. This is the standard equation for a circle centered at the origin with a radius of r, but our original equation was y equals the positive square root. This means the value of y must always be 0 or positive. It cannot be negative. Visually, what this means is that we only get the upper half of the circle. This is because every point on the graph must have a positive y coordinate. Here you can see figure 4.13, which illustrates this beautifully. It shows a semicircle in the first and second quadrants, with its highest point at 0 r. This represents the graph of y equals the square root of r squared minus x squared. Now, let's look at the key features of this graph. First, the graph is a relation. The equation defines a relationship between x and y. Second, the graph is continuous. This means it has no breaks or gaps. Third, it is symmetrical about the y-axis. You could fold the graph along the y-axis and the two halves would match perfectly. Its domain, the set of all possible x values, is from negative r to positive r, inclusive. Looking at the graph, you can see the horizontal extent is from r to r. The range, the set of all possible y values, is from 0 to positive r, inclusive. This confirms what we saw earlier. The graph never goes below the x-axis, and its maximum height is r. Finally, the graph is a function. This is because it passes the vertical line test. Any vertical line you draw on the graph will intersect the curve at only one point. This means that for every x value, there is only one corresponding y value. Now let's explore the second form, which is very similar to the first. This one is y equals the negative square root of r squared minus x squared. Notice the only difference is the negative sign in front. Let's see what this change does. Again, we can square both sides. We get y squared equals negative 1 times the square root all squared. This simplifies to y squared equals r squared minus x squared. Rearranging gives us the familiar circle equation. X squared plus y squared equals r squared. However, just like before, we must look at the original equation. It says y equals the negative square root. A square root is non-negative by definition, and multiplying it by a negative sign means the entire expression is 0 or negative. Therefore, the value of y must always be 0 or a negative number. This tells us the graph can only exist in the lower half of the coordinate plane. As shown in figure 4.14, we get a semicircle in the third and fourth quadrants. The graph's highest point is the origin, and its lowest point is 0 r. This is the graph of y equals negative the square root of r squared minus x squared. Let's quickly review the features of this lower semicircle. It is also a relation, continuous and symmetrical about the y-axis, just like its upward-facing counterpart. The domain is the same, from negative r to positive r. But now, the range has changed. Since y is always negative or 0, the range is from negative r to 0 inclusive. Finally, this graph is also a function because it passes the vertical line test. Again, for every x value in the domain, there is only one corresponding y value. We've covered the vertical semicircles. Now let's explore the horizontal ones. The general form is x equals the square root of r squared minus y squared. Notice that the roles of x and y are swapped compared to our first example. Again, let's square both sides to see the base equation. We get x squared equals r squared minus y squared. Rearranging it, we once again arrive at the standard circle equation. x squared plus y squared equals r squared. Now for the crucial part. The original equation states x equals the positive square root. This means the value of x must always be 0 or positive. It cannot be negative. This restriction tells us that our graph must lie in the right-hand side of the coordinate plane. It cannot cross the y-axis into negative x values. Figure 415 shows us this graph. It's a semicircle in the first and fourth quadrants, opening to the right. Its points extend from the y-axis out to the point, r0. This is the graph of x equals the square root of r squared minus y squared. Let's analyze the features of this horizontal semicircle. The graph is a relation, meaning it's a set of points related by the equation. It is continuous, with no breaks or gaps. This graph is symmetrical about the x-axis. The upper half is a mirror image of the lower half. The domain is from 0 to r, inclusive. The x values only exist in the positive half of the x-axis. The range is from negative r to positive r, inclusive. The graph spans the entire vertical range of the circle. Most importantly, the graph is not a function. Why? Because it fails the vertical line test. For example, the line x equals r2 would intersect the semicircle at two different y values. This means there are multiple y outputs for a single x input, which is the definition of not being a function. We've reached our fourth and final general form. It's x equals negative the square root of r squared minus y squared. This is the horizontal counterpart of the lower semicircle we saw earlier. As before, squaring both sides and rearranging the terms gives us the circle equation. X squared plus y squared equals r squared. The original equation has a negative square root. This means the value of x must always be 0 or negative. It cannot be positive. This restriction forces the graph to be on the left-hand side of the coordinate plane. Figure 4.16 confirms this. It shows a semicircle in the second and third quadrants, opening to the left. The x values on this graph are all between negative r and 0. This is the graph of x equals negative the square root of r squared minus y squared. Let's summarize the features of our last graph. It is a relation, continuous and symmetrical about the x-axis, just like the right-facing semicircle. Its domain is from negative r to 0. The graph never goes into the positive x region. The range is from negative r to r. The graph covers the entire vertical extent of the circle. And like the right-facing semicircle, this one is also not a function. It too fails the vertical line test, as a vertical line can intersect it at 2 points. So how do we put this all together to sketch a graph? The process has 3 key steps. First, always rearrange the equation to look like one of the 4 general forms we just learned. Second, based on the general form you've matched, you can determine where the semicircle is located, up, down, left, or right. Third, you'll need the radius. You can find this in the same way you would for a full circle, by looking at the r squared term in the equation. We've now completed our tour through the 4 forms of semicircular graphs. Let's quickly recap what we've learned. We started with the equation y equals positive or negative the square root of r squared minus x squared, which represents the upper and lower semicircles. Both of these are functions. Then we looked at x equals positive or negative the square root of r squared minus y squared, which gives us the right and left semicircles. Neither of these is a function, because they fail the vertical line tests. We also learned a simple 3-step process for sketching any semicircular graph. Simplify the equation, determine its position, and find its radius. This concludes our tutorial. Thank you for watching. Please subscribe to Math Zone African Motives for more tutorials. Let's work through some examples to solidify our understanding. We'll start with a straightforward one. Let's sketch the graph of y equals the square root of 9 minus x squared. Step 1 is to write the equation in the general form. Our equation is already in the form y equals the square root of r squared minus x squared. So we can compare y equals the square root of 9 minus x squared with the general form y equals the square root of r squared minus x squared. This tells us 2 things. First, because it's a positive square root of a term involving x squared, the graph must be an upper semicircle. Second, we can find the radius by setting r squared equal to 9. This means our radius, r, is 3. Now we have everything we need. We can draw our axes. Since the radius is 3, the semicircle will pass through -3 and +3 on the x-axis, and its highest point will be at 3 on the y-axis. The graph is symmetrical about the y-axis. The domain for this graph is all x values from -3 to 3. The range is all y values from 0 to 3. And yes, this is a function. Let's try an example that requires a bit more rearrangement. Sketch the graph of x squared plus y squared equals 16, where y is less than or equal to 0. Step 1 is to rearrange the equation to resemble a general form. We need to isolate y on one side. First, we subtract x squared from both sides to get y squared equals 16 minus x squared. Then, we take the square root of both sides, remembering to include both the positive and negative roots. So, y equals plus or minus the square root of 16 minus x squared. Now we incorporate the second part of the question, the condition that y is less than or equal to 0. Since y must be negative or 0, we must choose the negative root. Our equation becomes y equals negative the square root of 16 minus x squared. This matches our second general form. Comparing this to y equals negative the square root of r squared minus x squared, we determine the position and radius. The negative root means it's a lower semicircle, and r squared equals 16 means the radius r is 4. To sketch it, we draw a semicircle connecting 4, 0, and 4, 0, with its lowest point at 0, 4. This is the lower half of a circle with a radius of 4. The domain is from -4 to 4, and the range is from -4 to 0. Let's work through one more example, this time involving a horizontal semicircle. Sketch the graph of 9x squared plus 9y squared equals 81, where x is less than or equal to 0. The first step is to rearrange the equation. This one looks a little different. Since both terms have a 9, we can divide the entire equation by 9. This gives us x squared plus y squared equals 9. Now we need to isolate x. We subtract y squared from both sides to get x squared equals 9 minus y squared. Taking the square root of both sides gives x equals plus or minus the square root of 9 minus y squared. The question gives us the condition that x is less than or equal to 0. So, we must choose the negative root. This gives us our final form. X equals negative the square root of 9 minus y squared. This matches our fourth general form. Comparing it to x equals negative the square root of r squared minus y squared, we see that it is a left-facing semicircle, and the radius r is the square root of 9, which is 3. To sketch this, we draw a semicircle in the left-hand quadrants. It starts at 0, 3, passes through 3, 0, and ends at 0, 3. Its domain is from -3 to 0, and its range is from -3 to 3. This concludes our tutorial on sketching semicircular graphs. We've learned to recognize their 4 general forms, identify their key features, and follow a simple, step-by-step process to sketch them accurately. By following the 3 steps we outlined, rearranging the equation, finding the position, and determining the radius, you can confidently sketch any semicircular graph. The most common mistakes involve confusing the direction, like sketching an upper semicircle when the y value should be negative, or making a semicircle into a function when it should not be. Always double-check your initial equation to determine the correct sign for the square root. Thank you for joining Math Zone African Motives. We hope you found this tutorial helpful. Please remember to subscribe for more mathematical tutorials.